Professor Zensus, thank you once more for coming here for this interview. So I'm going to ask you a couple of questions about basically the personal side of the projects you have been part of in the last couple of years. What's your earliest memory of being fascinated by astronomy, and when was the point that you knew, all right, astronomy is what I want to study, that is the field that I want to dedicate myself to?
For me, the earliest time that I can think back of when I became interested in this field, astronomy, physics, astrophysics, mathematics, was as a school kid in high school. I was majoring in mathematics and physics, and I, like so many other kids, probably watched Star Trek and other shows like that about space. I saw the moon landing. I saw all the work that NASA was doing. I saw the German TV things about the explanations. That was my start. My start from being just merely another kid interested in physics to a kid interested in space.
How old were you when the moon landing happened?
Well, I was about 15 or so.
15, all right. And that must have been a big moment. I mean, it was a big moment, but for you personally, if you were already interested in it?
Well, it wasn't. I mean, just imagine something very big goes on, like we have these days, a World Cup or something. And here there was talk about people flying to the moon. I really had at that point, no good understanding of what was going on. But imagine, this was all the times when there was still black and white TV. It was very blurry pictures, and it took a while for the pictures to come back from the moon to the TV stations, and then even more time to show them to our TV sets. And so there was a lot of waiting, a lot of explaining what might be going on. But there was a certain fascination that something big had happened. And in everybody's life, and mine is no difference, there are moments that you don't forget. And so the moon landing was one of them, a critical point that I go back to and I remember.
So before this major breakthrough happened, before this picture was published of the black hole, what would you say is the motivating factor for you to go to work every day and to continue contributing to this project, to these findings?
There's probably many answers or many aspects to an answer to this question, but I like my work. I liked research. I basically got my dream job. And then after I graduated, I decided to go to the US for 1 year. But after 3 months, I decided this is what I want to do. I worked at Caltech, a fabulous university where lots of bright people were there. Lots of famous scientists were working there. In physics, Richard Feynman and his colleagues were there, and these were very approachable Nobel Prize winning scientists that walked around on the campus working with their students, and I just absolutely loved the combination of California and the science in such an incredible environment. I really liked the atmosphere, and that's why every day we would go to work. This is what made me go to work then. It was just fascinating, and I didn't just go to work 8 to 5. Astronomers work at night, and so we had to spend many weekends, many nights doing our measurements, doing our observations with telescopes, travel to faraway places where you're up all night using the telescope observing. Mm-hmm. I liked that. That became my personal life, and my professional life became intertwined in this way. And later on, I stayed in the US for more than 15 years. I didn't go back after a year. I made a career. I started a family. I met my wife. We had children later on. And so my life was very much in the US, and it was very much in the middle of nowhere in New Mexico, where I spent 6 years at the best radio telescope observatory in the world. And so this is the question: why do you go to work? Well, it's not work. It's a profession that we pursue.
We've talked about how you saw the moon landing. You were interested in math and physics in high school. You started studying physics. You were focused on, you started being interested in astronomy. You went to the US to focus on radio astronomy, and you started working at the Max Planck Institute, became a leader of one of the departments there. All these years, I would say, I mean, as an outsider, it looks like have kind of led up to this one enormous moment where these pictures were published or the results came in. What did that feel like for you personally, sitting there and seeing these results?
I have a hard time answering that because it didn't feel like this one moment. Everything you said is right. This is how this is my career. This is how things came together, with one exception. We did not know that we would have a guarantee to be successful. We did not know we would be able to do this. We also didn't work to this point, towards this point for 20 or so years. We work on a research field. We were working with our means on studying the centers of galaxies. We wanted to understand how they function, how they are formed, how they develop. And so we had ideas, we had theories. People like Stephen Hawking and Einstein and a number of other people had paved the way towards an understanding of black holes being relevant. But we didn't know that there was this one goal until relatively late, 5, 10 years, if you like, before we specified, well, this one experiment imaging the black hole in our galaxy, that would be just within reach. And we worked hard to do it. And we realized, as we did prepare for that, that's going to be very difficult. But this other galaxy, M87, which is very far away, relatively,
how far away is it?
55 million light years.
I mean, that's pretty far.
It's pretty far. So very far away, but it's huge. And so we did the calculations. They were from other observations we've done. We knew that this galaxy was in its center just about the right size for us to be able to make an image, possibly. So we started doing the center of our galaxy. We switched to this other galaxy, and nature was just incredibly generous to us by lifting the veil for a moment, perhaps, and allowing us to take this image. And we had sort of reached a point where we almost knew, well, we've come so far and we cannot go further because of technical limitations. And we pushed one step further and we were rewarded. My academic teachers already were working in this direction, already were making such measurements, and they didn't quite go far enough, they couldn't quite go far enough, but they also knew this is one day what we'd like to do. Look at the very center, see if these crazy guys, these astrophysicists, actually might be right. See direct evidence there is a black hole, a gigantic black hole. Now I'm talking about a black hole that has billions of masses like the sun in it, in a very small room. That's a crazy idea. You can't imagine, you can't really understand what it means to put these billions of suns into a region of the size of our solar system, which contains just one sun. So we thought, yep, we do this experiment, then one day maybe we get direct evidence through an image that this situation actually is the case. There is this huge mass in this central region. So this developed over many years, and our predecessors, so the whole thing, you could say, started 50 years ago when for the first time our method was proposed and actually done. This is another thing with science. Science is rarely an achievement of a singular person, but it is a step in a long process that sometimes can take decades.
So I'm sure that when you worked on the EHT on specifically the goal of imaging a black hole, in this duration, in this time, there must have been a lot of setbacks, a lot of technical difficulties, a lot of challenges that you had to deal with, but also as a person, just the human factor. You as a human, amongst many others working in this field, there must have been some things that felt difficult for you. What were the biggest personal difficulties that you had to deal with in your time working at the EHT?
To give you a feel for the challenges of the collaboration, just an example. We built the collaboration so that we also had ground rules for how to work together. And we needed those for doing the science work, the experiments, the criteria by which we we would critique and understand the results, agree on what the final outcome was. One aspect had to do with the publication, because obviously in a situation where you can potentially have a result as important as we thought we might get, we knew that everybody would be capable and would actually want to publish these results in the scientific journals as fast as possible. This is something we couldn't allow. We had to agree that no one from the collaboration would go out with these results before everybody in the collaboration would have had a chance to contribute to the writing of the papers, to checking the validity, and no one would be allowed to publish to the outside world the results. And we set up a press conference in Brussels. In fact, we set up 6 press conferences around the world, in Washington, in Brussels, but also in Taipei, in Taiwan, in Shanghai, in China, in Tokyo, in Japan, and then finally in Santiago de Chile. And lots of simultaneous satellite events that we ran. We knew these would be televised, and we had to insist that nobody would talk to the media and nobody would show this image. And we succeeded. We all showed the image 7 minutes after the hour, 3 p.m. in Brussels on April 10 for the first time. And immediately this image within minutes went around the world. At the end of the day, this image was the #1 topic on Twitter in the world. This image was on the Google front page for the next few days. And again, this image was on the front cover sheets of many, if not all, the newspapers around the world.
You have contributed to one of the major breakthroughs in astronomy and astrophysics in the last decade or so, probably even longer. I think this is a pretty big deal in astronomy. What would you like to be around to witness? What major breakthrough would you like to witness in your lifetime in astronomy, in astrophysics?
Well, I told you at the beginning, I started as a child watching Star Trek, watching the man on the moon. So I would absolutely love to see the first serious and solid result that we have made contact to an external civilization somewhere else. Being a Star Trek person, that would be something that I would love to witness. It's possible. One should aim at things that are difficult. It's possible, and so projects like that are underway. I'd be amazed if we would get some sort of a message, some sort of a signal that such a civilization exists and is able, through the exchange of electromagnetic signals, to communicate with us. Finding life on another system than Earth is a step towards that, but really making this communication, that would be great. And if I could be around to witness that, then I will not do a few more black holes like we have done. I'd focus on that.
So the Event Horizon Telescope has worked on a project. This project has resulted in an image of a black hole. I mean, it's the first direct observational piece of evidence of their existence. But, I mean, that black hole is 55 million light years away, right?
Correct.
Then I'm thinking, why should we care? I mean, what role does that result have in the scientific community? What role does it play for the problems of our lifetime? I mean, don't get me wrong, I'm not saying that it is irrelevant, but where do you see the role of them in the bigger picture of things, of humanity as a whole, if you will?
I think this is a very good and very important question, and I get it a lot lately, especially whenever I talk about millions of light years away events. So my answer to this is that basic research, fundamental research in science has shown time and again that it doesn't give necessarily a result in the short term, but in the long term it contributes to our basic understanding of the world, of nature, of physics, chemistry, biology, all the other classical fields. The basic research done in all of these has led to applications downstream that are possibly and at times changing the world. Think of the internet. The internet came out of developments at CERN. It has radically changed the world. The study of the sun, the energy mechanisms that make the sun shine, if you like, they have led to understandings of energy production, and they may help us in, at some point, finding new sources of energy that will solve our energy problems in the world. And you can have many examples where you do basic research with seemingly no application for the practical world, but then a time later they do lead into applications. Max Planck has coined the term, there is no application without prior understanding. So basic research contributes to the basic understanding of nature and the world, and I'm absolutely convinced that that is what we do need to solve the problems of the future. Einstein, 100 years ago, proposed the theory of general relativity, and scientists and the media were absolutely convinced no practical application. These predictions he made about the light being bent around the sun and so on, those seemed, well, nice ideas, exciting, but not relevant. Today, there would not be GPS navigation without us understanding the corrections that need to be made to the measurements of positions because of the masses of the bodies in the solar system that can be described by the theory of relativity. And so you need to be in for the long haul, but I stress you need to have the basic understanding to later on do high-level applications. And for us, that is going to be essential to go forward.
After the results get published, after the image got published, after the papers got published, I'm sure, I mean, vast majorities of the scientific community were interested in these findings, and also knew the weight of these findings, especially people from the STEM fields and people who are astronomy geeks. But because of the media attention, also a very broad audience was informed of these findings, and a lot of people know what a black hole is, or at least they have heard of the concept. Also, a lot of people find the idea of you know, the universe, the vastness of space, and the existence of such black holes fascinating, but might lack the theoretical fundamental knowledge that is maybe necessary to kind of group in, to kind of put your findings in a category. What would you wish that the broad, global, and maybe unscientific audience would take home from your findings?
I like to name three things that I think are relevant in a nutshell of what one might like to know. One point to realize is that we made a remarkable technical achievement by building a camera with radio telescopes, a virtual camera as large as the Earth. And this camera has a resolution that would allow us, transposed, standing here, but seeing your friend in New York on Times Square reading a newspaper, and you'd be able to see which page you'd be reading. That's the quality of the technical achievement that we have made. Mind-boggling. Second, more than 100 years ago, Albert Einstein, famous scientist, pop star of science, built this theory that very few people understood. Nobody thought was relevant for the future. Here we are 100 years ago, 100 years later, still making tests of this theory and still confirming it, still not finding that it's wrong on aspects of science. And so this theory is still valid. Thirdly, we look at this galaxy, and we find in the center of this galaxy, in a space that's only as large as our solar system, there's not one sun, there's not the mass of one sun alone, but there's the mass of 6 billion suns concentrated in the space, in the volume, roughly of the size of our solar system. That is a thing one should want to know, perhaps from what these guys in 2017 measured and published last year.
Just so I understand right, I'm not from the field, so I'm not super familiar of what a black hole is. From what I understood, it means that there is a point in universe where we have infinite mass at an infinitely small space. And that is why our traditional understanding of physics is no longer working. But right now you're talking of solar masses within this space. Does that mean that this understanding of infinite mass is wrong?
No, I'm talking about 6.5 billion masses in the size of a solar system, which is huge. 20 million kilometers, depending on billion kilometers, depending on how you measure it. So that's not an infinite point. The theory of the black hole says that yes, in the very center, the mass is in an infinitely small point. But this mass we're talking about is actually distributed, gravitating slowly towards that point. And it's at that point that the laws of physics as we have them now can't explain what's going on there. That's where we need possibly need a new theory to explain what's going on. But this mass is that we're expecting is in a volume that's much, much larger, but only of the size of our solar system.
Is there any message? Are there any last words that you would like to say towards our viewers?
I think we've given an example. We've given an example for how, towards a peaceful and purely intellectual means of understanding the world, as scientists, we're working together. In science, facts matter. Public relations, outreach, press conferences, and movies, and so on, they don't matter. What matters are the facts. And we were able to make a measurement and to give facts that support the theory that we've had before. So evidence-based research is an incredibly powerful tool that we can use in the basic sciences that we also should use in society to base our decisions on. And so these are times when obviously we don't get along very well in the world, haven't for thousands of years, but it's absolutely important that we do. And there's also times where often the validity of science as a basis for decision making is questioned. And I think if we can contribute a little bit to the understanding that doing science is important, basing decisions for society on scientific evidence is important, then I can say with this basic research, this bit of a result that we have made, this breakthrough in our field, we have also given an example for how we should work together as a people, as a society. I think that's important.
Beautifully said. Professor Zensus, thank you very much.
Thank you. It was a pleasure.